In this lecture, we examine the roots of polynomials, developing the rational root test. We're going to look more carefully at zeros of polynomials, and I'll remind you that a zero of a polynomial is sometimes called a root. Our goal in the next few presentations is to set up a strategy for attempting to find, if possible, all the zeros of a given polynomial. We will assume, for this section, that our polynomial has coefficients which are integers, or whole numbers. We will then set up some tests to run on the polynomial so that we can make some guesses at the possible roots of the polynomial and begin to factor it. The fundamental theorem of algebra tells us that a polynomial of degree n has n zeros if we include complex roots and if we count the multiplicity of the roots. We will be particularly interested in finding all the zeros for various polynomials of small degree, say n is 3, 4, or maybe the degree is 5. If the degree is 2, then the quadratic formula takes care of things for us. A rational number is a number which can be written as a ratio b over d, where both b and d are whole numbers. In this part of our lecture, we describe a set of all possible rational numbers which might be the roots of a polynomial. We will call this set of all possible rational numbers the rational test set. It will be a list of numbers to examine in our hunt for roots. It will be a list of rational numbers to test. Consider the simple linear polynomial, the degree 1 polynomial, 3x minus 5. It has one root, x equals 5 divided by 3. This zero, 5/3, is a rational number. Where did the integers 5 and 3 come from? The numerator is given by the constant term, and the denominator, 3, is given by the leading coefficient of the polynomial. This concept generalizes. If we're factoring a polynomial like this, where the leading coefficient is a sub n, and the constant term is a sub 0, then we can eventually write out a factoring of this form, where we have a product of linear factors. The product of the coefficients d1, d2 through dn must equal the leading coefficient a sub n, and the product of all the constants in these factors must equal the constant term a sub 0. So this tells us how to look for rational roots. This gives us the rational root test. If we have a rational number that's the root, where the numerator is b and the denominator is d, and if it's the root of a polynomial with leading coefficient a sub n and constant term a sub 0, then the numerator b of this root is a factor of the constant term, and the denominator of this root is a factor of the leading coefficient. The effect of this rational root test is that given a polynomial, we can create a test set of rational numbers that we'd like to try to see if they're zeros. Let's find the set of all possible rational zeros of the given function according to the rational root theorem. We'll do these three exercises. In the first case, we have a cubic polynomial where the leading coefficient is 2 and the constant term is minus 3. So the roots are going to be limited to fractions whose numerator divides 3 and whose denominator divides 2. Now the integers that divide 3 are just 1 and 3. And the integers that divide 2 are 1 and 2. So all of these fractions are going to have numerators 1 or 3 and denominators 1 or 2. This gives us 1 over 1, 3 over 1, 1 over 2, and 3 over 2. If we recognize that the roots might be negative, then we have this set of 8 numbers, plus or minus 1, plus or minus 3, plus or minus a half, plus or minus 3 halves. Let's go on to the next problem. In this case, the leading coefficient is 3, and the constant term is 5. So we're going to have fractions whose numerator divides 5. In other words, the numerator of these fractions is 1 or 5, and whose denominator divides 3. The denominator will be 1 or 3. So my possible test set will include plus or minus 1 divided by 1, plus or minus 5 divided by 1, plus or minus 1 divided by 3, plus or minus 5 divided by 3. One more example. Let's look at the rational roots of this polynomial whose leading coefficient is 6 and whose constant term is 35. So we're going to look at fractions whose numerator divides 35. What are the integers that divide 35, 1, 5, 7, or 35, and the denominator needs to divide 6. What integers divide 6? 1, 2, 3, or 6. So the numerators will be 1, 5, 7, or 35. The denominators will be 1, 2, 3, or 6. That gives us a pretty large set, particularly if we throw in plus or minus signs. But that this set at least is finite, and we could begin testing some things from this set. In the next presentation, we will work through factoring a fifth-degree polynomial, and as we go, we'll discover upper and lower bounds on the possible zeros of a polynomial.